The ocean. So if you've been to the U.S. Center, and I want to see a show of hands, who here has been to an event at the U.S. Center over the last week and a half? Thank you for coming back. That's great. And to all those who have not raised their hand, thank you for coming. It's great to have you here. We've talked a little bit, at least tangentially, about the oceans and reflecting on the ocean's problems a little bit across a wide variety of panels so far the last week and a half. But I'm really excited for this one in particular because we're going to take a little bit of a deeper dive into some of these problems that we've talked about, at least on a slight level, but we're going to get a little bit more into what that actually means. What do these problems actually mean for the oceans, and what do they mean for us? Because when we talk about the ocean problems, we're really talking about a global problem. A healthy ocean in the future means a healthy planet, and that's important to remember. So again, that's why I'm excited to have this discussion here this morning, because the oceans are so important, but also because of just who we have on our panel today. We've talked a lot about youth involvement here at COP-21. In fact, the first event we had at the U.S. Center focused on youth involvement. And today we have a group of early career scientists, grad students. We have a postdoc who just defended October 1st, so congratulations on that. But these are the folks who are in the future are going to be doing the research, going to be monitoring our oceans to find out what exactly is happening, what is changing, and particularly looking at, furthering our understanding of the oceans and its impacts on our atmosphere and its impacts on us. So without further ado, and in lieu of having me kind of introduce all of them by myself, I'd like to start off with a question I want to ask to each of our panel. And that's basically to introduce yourself. Why did you get into this field? What are you looking at? How did you find that the ocean is what you wanted to study, and what drew you to that when you first became at least a scientist? Go ahead.
Hi, everyone, and thank you so much for having us and having young scientists as part of this event and as part of the conference of the parties. My name is Yassir Edebar. I am a fifth-year PhD student in oceanography at Scripps Institution of Oceanography. And how I got into the field that I work in, which is climate science and the role of the ocean in climate, I've spent a lot of my childhood near the ocean, in the water, doing water activities, and always wanted to stay near the ocean and understand it. And so throughout my entire academic career, I've sort of veered towards understanding how ocean processes, environmental processes work, and found myself doing a PhD in oceanography at Scripps that overlooks the ocean, so I couldn't be happier. My research is mostly on how the ocean and the atmosphere interact with each other and how that relates to biogeochemical dynamics. These are the carbon cycle, the oxygen cycle of the ocean, which plays a huge role in our climate and even in discussions here at the conference, the parties. So.
Hello, I'm Amanda McCarty. I work for the National Oceanic and Atmospheric Administration in the United States. I'm a little different than some of the other panelists in that I've finished my graduate work and I now work at the interface of science and decision making. I'm originally from Minnesota, so if anyone knows where that is in the United States, it's in the very middle of the country. It is about as far from the ocean as you can get. And so becoming a marine biologist was something that didn't seem like a possibility when I was growing up. I sat in a 7th grade classroom right in front of this beautiful aquarium with these brightly colored fish, and I couldn't believe that something like that existed. And as I learned more and more about these amazing places on the earth where things like that could live, I got more and more excited. And so I made a trek across the country to the state of Washington to study for my undergraduate, and then did a graduate degree in marine biology to continue learning about this really important place in our earth. And so now I'm done with my graduate work, and I'm working in the agency trying to make that science useful and help inform decisions.
Hi, I'm Natalia Gallo. I'm also a PhD student at the Scripps Institution of Oceanography. I'm a biological oceanographer there. And I started studying marine biology because I think it was my joint interest in just how how biology works, why certain animals live in certain places and not in other places, just this innate fascination with biological systems. But also I was really interested in how we as humans use our marine resources and our marine environment. So at Scripps, I'm working on ocean deoxygenation and the impacts of oxygen loss for marine ecosystems. Particularly, I focus on how oxygen gradients affect fish communities, so which fish can live under which kinds of oxygen conditions, and which kinds of fishery species can live under which kinds of oxygen conditions.
My name is Kaitlin Loud, and I'm a second-year PhD student at the Scripps Institution of Oceanography at UC San Diego, and I study marine biology. And like a lot of other marine biologists, I found my love for the ocean at the beach, but in between those trips, I was in a landlocked state, and I was reading a lot of National Geographic, and it was reading that I found that science is actually happening every day, and you can discover new things. It wasn't all in a textbook, and that was really exciting for me. And so I also knew that I wanted to do the kind of research that people would be interested in reading about in National Geographic. And so in college, I discovered that I have a love for crustaceans, like crabs and shrimps and lobster. And I think they're really neat because they waddle around with these shells, and whenever they want to grow, they just throw them off and make a new one. And luckily for me, people also really love crustaceans because they're delicious. And in graduate school, I began studying crustaceans and how they interact with ocean acidification, which is what happens when carbon dioxide dissolves into the water and changes the chemistry. The pH lowers, basically it becomes more acidic. And I'm lucky to join in a community that shares a lot of data with each other and makes sure that young scientists like me are learning how to collect the best data.
Hi, I'm Matt Siegfried. I'm a postdoctoral scholar at Scripps in Dr. Helen Fricker's lab. And our lab is made up of physical glaciologists. So we all try and understand how ice sheets and glaciers move and how they're changing through time. My route was a little more wandering. I don't have a great creation story like they all do. I did earth science as an undergraduate, and I actually did geochemistry, which is really far from what I do now. And then when I finished up my undergraduate degree, I've always loved the earth, and I wanted to continue studying it. And glaciology was the one thing I didn't really have any experience with. It was kind of a mystery to me. And really, the glaciers, for everyone that don't get out there and see them, they're kind of mysterious, these big blocks of ice. And so it was the mystery that really drove me to glaciology. And actually, interestingly enough, they're still kind of mysterious to me. I study how water beneath Antarctica moves around, liquid water, where it is, and how that affects ice flow. I also study how the ocean and the ice sheet interact and how that changes the ice sheet behavior. And kind of the whole idea behind this is understanding these ice sheet processes a little bit better so we can project how they're going to change into the future. When an ice sheet melts, that water needs to go somewhere, and usually it goes into the ocean. And so that contributes directly to sea level rise. I work in West Antarctica in that in West Antarctica, you have the potential for just over 3 meters of sea level rise, so that's 10 feet. That would be a big problem if West Antarctica goes away, and so those are kind of the questions I'm interested in.
All right, thanks everybody. And as moderator discretion, I will also say I also love the oceans, but funny enough, I get seasick unbelievably easy. So I like to look at the oceans from the comfort of the beach and or a computer screen. I am a forecaster at the Climate Prediction Center. We are the folks who put out monthly forecasts for the El Nino Southern Oscillation, including what we are experiencing right now, a strong El Nino. So I love the ocean. I'm really excited to have all you guys here today. I think I know what Matt's answer might be for this first question, but the first thing I want to ask all of you this morning is, what is the one concerning aspect of our ocean's future with a business as usual scenario that concerns you? What is that one thing that you kind of go back to when we talk about climate change in the oceans, which worries you?
I think before we actually address the future impacts of greenhouse gas emissions on the ocean, we have to address first what the role of the ocean is in current climate. So the ocean essentially regulates our climate. It's because of the ocean that we have nice, livable climate, for example, in Europe and in North America. And they also play a central role in climate change. Without the ocean, climate change would have been very different. So they absorb about 90% of the heat trapped by greenhouse gases. Because the oceans are huge, they're dynamic, they circulate, and they have a high heat capacity. Water has a very high heat capacity, so it's able to take most of the heat that's trapped by CO2 and other greenhouse gases and circulate it around the ocean. Without the ability of the ocean to take up heat, I think our climate would have warmed by way too many degrees Celsius than what we have today. Next, the ocean is also a huge carbon sink. It absorbs about 30% of CO2 emissions. And these services, these carbon uptake and heat uptake, don't really come at no cost. And an excellent way to sort of portray this is future emission scenarios impact on the ocean. We expect that the ocean would still take up most of the heat, so that's going to warm the ocean. We also expect it to become more acidic. The more CO2 we put in the atmosphere, the more that goes into the ocean and makes it more acidic. And finally, this is a really interesting new phenomena that Natalia has described as ocean deoxygenation, which is essentially ocean oxygen loss. As the ocean warms, it starts to lose its oxygen for two different reasons. The solubility, which is the amount of oxygen that the ocean can hold, decreases with temperature. Warm water would just leave oxygen out into the atmosphere. But also the ocean becomes more stagnant when it's warm. When you warm the top of the ocean, it becomes less dense. And so deeper waters that usually have microbes that respire in the deep ocean become deprived in oxygen. So those waters can't really make up as easily to the top, and it becomes hard for that water to become ventilated or resupplied with oxygen. And so those three different topics, ocean warming, ocean acidification, and ocean deoxygenations, are going to be the three main impacts on our oceans, and it's really important that we actually address these within the policy debates and within our conversations about climate change in general.
That's very true, and I'm interested in how those impacts are going to actually affect our ocean life. We love them because we eat them for food, and we also enjoy seeing them out in the natural environment. So oceanification is probably going to affect very many species, not all of them in the ocean, but a lot of them. We expect decreases in pH or increases in acidity across the oceans, although that's spatially variable. But in terms of the impacts on ocean life, shellfish have been shown to be largely negatively affected. These are animals like mussels and oysters that we rely on for economic benefits. So that happens because when these changes in ocean chemistry come around, it makes it harder for animals to make their shells because the building blocks aren't there with these changes in ocean chemistry, and the water actually becomes corrosive. So you can imagine if you're trying to frame a new house and you get halfway done and then you realize that there's no more lumber around, and while you're searching for that lumber, the other half of your house is decaying. This is something that animals in the future ocean are going to be contending with. In terms of crustaceans, which is what I study, there's not a whole lot of information. We're still learning, but largely it seems that they may not be affected, or they may actually increase calcification under these conditions. And so we're still studying what this means for them. Is it a good thing? Is it a bad thing? Is it neutral? So my interest is in the California spiny lobster, which is a large fishery in Southern California and down through Baja, Mexico. So I'm interested in how oceanification affects their exoskeleton of their shell. From their name, they're obviously very spiny, but they use their exoskeleton for other defenses too, such as making sure that octopus don't come along and just take a really large chunk out of them. So it's important to study these things because, like I said, they're very important fishery species. We want to know how we're going to be able to manage these populations in the future. So hopefully with work like mine, we can understand how they're going to survive, how they're going to grow, and what we're going to be able to do with them in our future oceans.
All right, I'm glad we touched on this a little bit. I think one aspect that we kind of gloss over a little bit is this idea of how does an increase in greenhouse gases in the atmosphere end up translating into impacts to the oceans. We've heard about ocean acidification, deoxygenation, but also specifically talking about the poles as well. How do we see this impacting the oceans? How do we go from the atmosphere to the ocean and then finally see those impacts spread out across the globe?
So a lot of the impacts at the poles are moderated by the greenhouse effect, which we all hear about here. So more CO2, more greenhouse gases, the atmosphere warms up. as Yasir was talking about, that also warms the ocean. Actually, it warms the ocean more than the atmosphere itself. And so if you think about where ice sheets are, which is what I study, they're right in between the ocean and the atmosphere. And so you're kind of melting these ice sheets from both ends. And so from the bottom, you have this warm water that can melt ice just like, you know, an ice cube melts in your glass. But unlike an ice cube in your glass, it's like you're actually dumping more and more ice into the glass itself. From the atmospheric side, the atmosphere doesn't have the heat capacity of the ocean, so it doesn't have as strong of an effect, but you can get these really interesting feedbacks where, say, if you start getting melt on the surface of a glacier, that water can propagate through the ice sheet, and on an ice shelf that could cause a catastrophic collapse, and we've seen that happening on the Antarctic Peninsula. I think they showed some pictures of that in one of the NASA Hyperwall presentations, and that can cause your ice behind it to accelerate, like a cork being released. And then on the ice sheet itself, when you get that water to the bed of the glacier, water is very slippery, which we all know, and ice slips on water just like we slip on water. And so if you get more water at the bed of a glacier, you can speed up those glaciers significantly. And we see that in Greenland right now. We see that in mountain glaciers right now. And that could start happening in Antarctica if it gets warm enough in the atmosphere.
Can you touch on just a little bit this idea, though, that even if we stop emitting now, we're still built into the system, at least with this. I mean, when glaciers start to move, it's going to take a lot of people. You can't just get in front of it and stop it. So can you go a little bit more into that?
Yeah, so we like talking about near-term commitment to sea level rise. It's kind of one of those catchphrases we have in glaciology right now. And what it means is that the ice sheets respond on all kinds of timescales. They can respond on very short timescales, on just a daily timescale, but they also respond on timescales of years to tens of thousands of years. And so if you change something on the flank of the ice sheet, that propagates upwind into the interior of the ice sheet over the course of thousands of years. And we can't change that, really. We already committed to that. And so even if we stopped right now and cut off all of our emissions, the ice sheets are still going to respond to the greenhouse gases that we emitted last week, last month, last year, over the last millennia. So it's really an interesting predicament we're in right now with the ice sheets.
Yeah, and if I could just add a little bit, the biological component of ocean deoxygenation. So Yasir spoke about how physical factors, so reduced mixing in the ocean, are leading to this decreased supply of oxygen in the ocean. But also biology is very, very sensitive to temperature. So when you're getting an increase in ocean sea surface temperatures, you're actually increasing biological oxygen demand. And in just 1 milliliter of seawater, there's over 1 million bacteria, and all of those bacteria use oxygen. So when you increase the temperature, all of the animals in the ocean are starting to breathe more. And this is an important reduction in oxygen. And so it's really this imbalance with oxygen supply declining and then oxygen demand increasing in places. And we, for example, if we have a 10% reduction in oxygen in our own blood, we experience very significant medical effects. We know this with high altitude sickness, when people have strokes, and in some waters off of California in the subsurface areas, they've actually seen 20 to 30% reductions in oxygen already just in 25 years. So these are really large reductions in oxygen that we really need to make sure we're studying. And I think that one of the things that concerns me is that this is actually a pretty new impact that not too many people have talked about.
So you've heard a lot in response to this, and I think it's sometimes helpful to get a summary. One of the things that my agency has done with a broad community is to conduct a national climate assessment to try and understand the impacts of climate change on various sectors, including the ocean. And what the National Climate Assessment says about oceans is ocean waters are becoming warmer and more acidic. This is broadly affecting ocean circulation, chemistry, ecosystems, and marine life. Rising sea surface temperatures have been linked with increasing levels and ranges of diseases in people and marine life. And so one of the things that I think is really important to think about is we often talk about what's physically changing in the system. A couple degrees here, a couple degrees there, no problem. what happens when you get a temperature change of a couple degrees in your body? You know, and even the acidity. Oh, it's just a little bit more acidic. Well, what happens when you have acid reflux, you know? The ocean can't just take some acids in the same way we can. And so it's really important to think about how that cascades from physical impacts to ecological impacts where different species interact differently. And we're one of those species as humans. And so there are going to be a lot of impacts on the food we eat, the ability to go to the beaches in terms of things like harmful algal blooms where there are toxins that are produced because water temperatures are different, circulation is different. It's not just a physical change, it's really a change in the way we interact with the oceans. And so that's one of the horrifying and exciting things about the work we're doing is that if we can understand these changes and we can try and manage them as much as possible, we can hopefully maintain the strong relationships we have with the ocean.
Thank you for that, Amanda. And I think it's an important thing. We're currently under a global chloral bleaching event right now, thanks not only to El Nino, but just about how warm our oceans are pretty much everywhere this year. And, you know, getting into this idea of harmful algal blooms, we've had a pretty substantial harmful algal bloom all over the West Coast, stretching from the Gulf of Alaska all the way down to California for the better part of the last 6 months, at least in some areas, from roughly May until now. And you know, when we have El Nino events, we tend to see these harmful algal blooms in the West Coast occur in the spring following the event. Not often do we see them during the actual event. So there's a lot going on in the oceans right now, and I think this leads into a very important aspect. We're talking about how the oceans are going to change in the future, but we're all talking about in the future. The important thing is, how do we know how they're changing? How do we monitor the oceans? The ocean is a vast, vast area, and we don't have houses on the oceans besides, I guess, houseboats close to shore. But how do we monitor? How are we monitoring now, and what are some of these ideas of how we're going to monitor the changes in our ocean in the future?
At a high level, we collect observations from satellites, we collect them from buoys, we collect them from tidal measurement gauges. There's many ways that we collect information about the oceans. There are special places in the oceans. In the U.S., we call them estuarine research reserves and marine protected areas and national marine sanctuaries where we collect information about a specific place and try and integrate it into a meaningful way. It's often very expensive to monitor in these ways, so we're looking at very innovative ways of monitoring using autonomous underwater vehicles, trying to figure out ways to take these robots, essentially, we have called Argo floats, and get them to go deeper into the ocean to understand what's going on in areas where satellites can't see or boats can't float. And I think our panelists here have more details on some of these, so I'm just going to give that high-level summary and then pass it off down this way.
That was a fantastic summary, and I actually rely on NOAA for a lot of the data that I need, too. In terms of ocean acidification, that's traditionally been monitored on the coast where we take water samples and via shipboard measurements, which can be time-consuming and also a little bit expensive. So what we're looking for now and what we really need is sensors that can be deployed across the ocean so we can monitor the spatial variability and understand what's going to happen in the future. Something that we do in the lab, we take that data, we understand what's happening in the environment right now, and then we use the best models that we have to understand what's going to happen in the future. And so then when I set up experiments, I set up those future ocean levels in small tanks and then subject my animals to that for a period of time in the best way that I can do. And then I choose what to measure, like survival or growth. How are they doing under these conditions? I believe something in our future, what we're moving to in this field is being able to understand the functional impacts. So not just how they're surviving and growing, but what changes in calcification might mean. Can they still defend themselves? Or do they produce changes in genes that might be interesting for us to look at and then study in other species, too, that have the same genes?
To add on to this, and you really brought up a very important point. Observations is the basis of everything that we do, including policy making that many of you are involved in this room and on the web. For us young scientists, the biggest challenge to making our science and doing research is finding robust observations. Why is that? It's because climate change is a global and long-term problem. So it requires global observations and very long time series that span decades and a century. And so it is really important to maintain this, this importance of observations both within policy and scientific planning. For me, personally, I use climate models and observations to understand how the ocean works. And Argo floats are hugely important. These are little floats that are about 1.5 meters big, and they go all the way down about 2,000 meters to the deepest, to about 2,000 meters of the ocean. And they come back up and measure temperature and salinity. And there's about 3,900 of them today. And it's an amazing example of scientific achievement. Really, really amazing how we can all collaborate. I think it's about 30 countries that collaborate in Argo. There's a variety of other observation systems that we also use to get an understanding of both ocean atmospheric changes. And I think it's really important for policymakers, for people throughout this conference to make sure that we observe the climate system, because our adaptation and mitigation is truly dependent on that information.
Yeah, I would like to add that the ocean is a really challenging place to actually get enough data, because not only do we need good spatial resolution, and again, the oceans cover 71% of the world, we also need good vertical resolution. So things aren't the same at different depths in the ocean. This is especially important for changes in oxygen, changes in temperature, changes in pH. So I work in the lab of Dr. Lisa Levin at Scripps, and so one of the things that she's employed is using these natural laboratory systems. So we go to the ocean, to places where there are natural strong gradients in oxygen, in pH, in temperature, and we look at which thresholds dictate different changes in community composition. And by doing so, we can learn how, as these different thresholds for temperature, pH, oxygen change in the future, what sorts of changes we then predict to see in the ecosystem. So using these natural gradients to allow us to predict out into the future.
They have it easy. They don't work at the poles. So at the poles, especially Antarctica, we didn't have satellite data for a long time. We couldn't see 90% of Antarctica from a satellite until 2003. We had pictures of it, but we didn't have the high caliber data we needed to assess how Antarctica was changing. So in 2003, NASA launched ICESat, which really changed the way we looked at Antarctica a lot. It could measure the height of the ice sheet to kind of 10 centimeter resolution, so about that big. And since then, we've been what we call it closing the polar hole. So our satellites have been seeing more and more of the continent, and we need to continue that into the future to be able to monitor the ice sheets. Another big issue we have is satellite missions are expensive and they don't come around often. And sometimes there are gaps between satellite missions. And so to tie together these long time series we really need consistent satellite measurements. ICESat-2 will be launched in the coming years, and so that's going to be a big deal for us. There's a joint NASA and Indian Space Agency project to launch NISAR, which will tell us the velocity of Antarctica in details we've never seen before. So there's some really exciting satellites being launched to look at the poles, but we need more of them. Another issue we have is we have these great satellite measurements, but it's hard to look kind of at the finer details using that. And so we really need to span spatial scales by using ground data, so going out to Antarctica and collecting data, using airborne measurements like Operation Icebridge from NASA, and satellites to really get all the details we need to be able to monitor in the future.
Yes, and just one last thing to add. So good spatial resolution, good vertical resolution, but also good temporal resolution. So we need a good baseline, and then we need continuous monitoring to see how these environmental variables, how these biological communities are changing with time. This is very time-consuming and cost-consuming, but it's very important if we want to understand how the ocean is changing with climate change.
So we talked a lot about kind of indirect measurements, satellites and then other buoys, but some of you go out there and take these measurements yourself, right? Is that true? Can you get a little bit more into that? What are field campaigns like?
So we go out to sea. Some people go out for a day, some people go out for a week, some people go out for months at a time. And we actually use sensors. We deploy sensors. We collect data. Sometimes we collect water samples and then analyze those water samples. I work both with benthic trawl sampling techniques to look at what biological communities you have living on the bottom. And I also use non-destructive methods like remotely operated vehicles where you can actually look at what lives on the bottom in a non-destructive method. And that really allows us to link together the environmental factors and the biological data.
So I spend most of my time taking care of experiments in the lab, but there are some days where I get to go out and look like a true marine biologist out there in the tide pools, snorkeling and things like that. Currently what I'm working on is collecting environmental data for my next experiment. So I'm understanding how pH actually changes over the course of a day. So I'm out there at dawn, middle of the day, evening, and then the middle of the night to collect my data. And it's actually very exciting. I enjoy getting out there and being able to see what the ocean is doing and getting reconnected to that.
10 days ago, I was in Antarctica, and some of the pictures up there from this past field campaign, it's hard work down there. I've been down there 5 times, but it's worth it to collect this data that gives us insight that we've never seen before. So one of the projects I work on is we basically just put GPS on the ice sheet, and then it's no different than your phone. It tells you where you are, and then we can use that to look at ice velocity. But we're getting ice velocity every 15 seconds, whereas with a satellite, we get it maybe once a year. So it's giving us really incredible fine resolution, and we're seeing the ice sheets change on timescales we never really expected them to change on. If you want to know more about life in Antarctica, I'll promote myself a little bit. And I just got done doing a field blog specifically to answer this question of what it's like to be in the field. It's very unique, and it's a really cool experience. So that's on nature.com. Sorry.
Excellent plug of your blog. ENSO blog also at the Climate Prediction Center, climate.gov. I recommend it for all your ENSO needs and El Nino needs. Before we get into our last question, I want to go back to this idea of impacts. We're talking a lot about, Antarctica and the poles and their impacts, but I mean, the ocean, it's connected. It's one big ocean. When we're talking about this. So can you just kind of give us the broader scale picture here of terms of impacts? How does your topic, I guess, impact the globe? If that's a broad question, I understand.
I'll take it quickly because we'll go from the poles to the equator, I guess. So the ice sheet adds water to the ocean. So we're talking sea level rise. But sea level rise is not fair. So Antarctica is going to shed this mass into the ocean, but the sea level in Antarctica is actually going to go down, which is kind of crazy to think about. So the ocean redistributes based on the pull of gravity, Earth's gravitational field. And when you lose mass from Antarctica, it has less of a pull on the ocean water. So actually, Antarctica, sea level will go down. What does that mean? Well, it needs to go up somewhere else. And so the northern hemisphere, if Antarctica loses mass, the sea level will go higher than just the mass that was lost from Antarctica. And so it's actually a slightly more complicated story than we like to think about. It's not just the entire ocean is going to go up by this much, but different places are going to have different impacts. And that's a really interesting thing to think about. And it's really not fair of the ice sheets to do that to us.
Yeah, I just wanted to add from the perspective of biological communities changing. So we as humans, we depend on the stability of marine ecosystems. Our coastal economies have developed being used to relying on oceans to do certain things, provide us with fisheries, provide us with tourism. And the truth is, right now, a lot of the biology in the oceans is rearranging. Species are moving into new areas because of changing temperature, changing oxygen. And so really, it's our reliance on marine ecosystems that's going to be impacted. Nature is going to figure out a way to change with the ecosystem changes, but it's going to be much harder for us to be able to rely on the ocean for the services that are really necessary for coastal economies.
Natalia hit on something very interesting, which is species moving with temperature. In terms of fishery species, the Maine lobster at the southern end of its range has actually been moving up higher in latitude. So fishermen that are used to going out and fishing aren't finding the lobster where they used to. And then Governor Inslee from Washington has been here the past couple days, and he knows very well the impacts of oceanification actually on the coasts that are happening right now. So in Oregon and Washington, the fisheries or the aquaculture for oysters and mussels are very important there. But a couple years ago, the people who were growing these started seeing that the young animals weren't developing properly. And so now we've learned that ocean pH is actually changing in that area, and they're seeing the impact. So they're having to grow these animals actually in the laboratory before they bring them out into the ocean and make sure that they're buffering the water in the laboratory so they can actually grow.
I don't think I have much more to add than all of this. This is an excellent summary, but I guess to make it more relevant to policymakers and to the discussions you have in the negotiations room, some of you I see have red tags, and so you're probably involved with INDCs or figuring out the long-term global goal of 2 degrees Celsius, 1.5, 3 degrees. So it's really important to know what the global impacts on the oceans are for these different scenarios. What does the ocean looks like at 1.5 degrees or 2 degrees Celsius? Because it's not as healthy as what our climate would be on land at 2 degrees Celsius, and we really depend on the ocean. A crucial and critical point that I think has been overlooked for quite some time is the ability of the ocean to take up heat and carbon in helping us mitigate climate change. So in the future, the ability of the ocean to absorb carbon is going to be weakened, or expected to be weakened. So when we submit these INDCs and have these targets, we have to take into account the ability of the natural world to mitigate climate change as well. And so that's another impact that we have to think about in the future from a policy perspective, and that scientists can actually help inform the policy process.
And just one other really quick addition to that, I think thinking about environmental feedbacks is really important. And so with the expansion of oxygen minimum zones driven by oxygen loss, these oxygen minimum zones are actually carbon maximum zones, are very high in carbon dioxide and also nitrous oxide, which is a very potent greenhouse gas is produced in these areas. So the ocean can actually become more of a source of greenhouse gases as you get an expansion of oxygen minimum zones. So really thinking about how the climate change impacts in the ocean may change the regulating role the ocean plays in our climate system.
And I will just end by saying that, on this question at least, by saying that, building off of what's already been said and saying that coastal ecosystems provide many services to people, and they provide many climate services. They are the foundation of many communities and individuals' lives and livelihoods by providing food, by providing tourism, and whenever an ecosystem changes, the ability that we have to depend on that system also changes. From the mitigation side, coastal ecosystems store massive amounts of carbon. They pull massive amounts of carbon out of the air. And if we're chopping down mangrove forests for other purposes, we lose that carbon very rapidly. And so we have to think about the many services these ecosystems provide from a climate perspective, but broadly from a supporting our communities and economies perspective as well.
Thank you for that. It's an important point to make. Everything is connected. It's not like we can attack all of these things independently, because it's much more complicated than that. All these aspects, not only from the open ocean to coastal areas to coastal economies, it's all tied together. And that's an important point to make. So I want to end with this one question before we open it up for Q&A. On a more hopeful note, I want to say, as early career scientists, what is the most inspiring aspect of what you're doing?
So for me, it's the fact that we're in an era where scientists can begin to communicate their science. I love going out into the public and being able to talk about the spiny lobster species that I study, because so many people go out and fish it every year and understand what it's doing. So the fact that we can actually come out here and begin to talk and share our science is important, because we spend a lot of time reading papers, researching, and then talking among each other to share our ideas. I can do something to help fix oceanification, ocean warming, deoxygenation. You all can do a small part, but the fact that we're here and we're making an agreement on a global scale is important, because these are all very global problems. So my challenge to you during this COP-21 and in the future is to put me out of a job. Help me fix this problem.
I think that one of the really inspiring things for me is that we're seeing young scientists get training to communicate their science in a way that's effective to policymakers, especially because I think it's really, really important that as scientists we understand how policymakers use our science to make good informed decisions. And I think the more we can communicate effectively and get out there and talk to policymakers, the better the decisions will be in terms of reflecting the best science. And that's really exciting that we have that training now.
So I work with models, and learning how the climate system works is pretty much what keeps me motivated as a scientist. Just knowing how the ocean works, how the circulation interacts with the biology and chemistry and geology of the ocean is priceless. There's nothing more amazing than knowing how our natural world works, at least for me, and how it relates to society and how it benefits society, I think, is a really special and unique thing in scientific careers, and I recommend younger generations to pursue such path.
So I'll answer this slightly differently. I got into this whole game because I like being outside. Being outside is amazing. It's beautiful out there. And look at those pictures. That's our job. When we go out into the field, it's the most inspiring part. We're seeing the beauty of the earth, and it makes me really want to understand it more. There's just nothing like waking up, unzipping your tent, and seeing the Transantarctic Mountains, a mountain chain that we only started knowing about 100 years ago. It's easily the most inspiring for me.
So I'm an idiot, and I left that world. And instead of wearing a wetsuit every day, I wear a suit like this. And sometimes I think about going back, because I agree, it's the beauty of the world we live in. And I think sometimes we spend so much time staring at computers that we forget how amazing the world is, how unique the balance is that we've been able to achieve on this planet between species, between the physical environment, the biological environment. And there are so many questions still to be answered. So from a science perspective, we will never fully understand this planet, and that's exciting. Why I did make that jump into wearing this suit instead of a wetsuit is because of the need to translate science into decision making, and because I really want that world to continue to exist. I want to be able to walk outside and still see that beauty. And I know that that means that I have to help make the science useful to people. So that's what I love, is every day I come in and I read things that people like these amazing scientists are producing, and I try and translate that into something that's useful to policymakers, and occasionally I get to make a little policy myself.
Thank you very much. I do want to say, as someone who also just spends most of his day looking at a computer screen, I understand how much we'd much rather be outside looking at nice, fancy things. We have about 15 minutes left, and I will walk around with this microphone. If you want to ask any questions, please do. And we'll probably take a couple at a time, and you guys can answer them as you see fit.
My name is Judy Soul from Cape Town Television and South Africa Satellite. My question is there any way that you also study what to do about the problems that you're seeing, like ocean acidification? Is there any recommendations that you can make that change it, or is it just saying you're just watching us plotting the course of it all going down?
Thank you very much. You have given us very good exposure of an unknown environment, which is actually, I think the oceanographic science have been started in 50, 60 years ago. I would like to ask you one question and one comment, which is a political one. I haven't heard upwelling phenomena from you, El Nino, La Nino, and the extreme pressure in the deep seas. Do we have, for example, tools that can go as deep as to the floor of the sea? Because I think it's a wrong concept for me. I think somebody told me that if you go depth, there is no any tool in the world that can go the deepest point of the seas, because of the pressure that can extremely destroy any tools, any materials. And the comment is, you have convinced us the importance of the sea and the ocean. Can you convince this to your congressman and to not to block the outcome of this conference, which is founding a legally binding convention? Thank you very much.
For the first question about El Nino, first point on El Nino and La Nina, I will say El Nino and La Nina are interesting in a climate change perspective, because we always talk about El Nino as a warming of the equatorial waters in the Central and Eastern Pacific Ocean. But it really relies upon not only the warming there, but the cooling in the Western Pacific Ocean. So just because we raise the temperatures of the oceans during climate change doesn't necessarily mean we'll see an impact on El Nino itself. That's not to say it can't be. It's still an active research question. But what climate change does do with El Nino and La Nina is that when we see impacts atmospherically from those ocean responses, those atmospheric response can certainly be impacted. So we do know that the warmer the atmosphere, the more it can hold water. And if El Nino means we tend to see more rainfall over, let's say, California, and it's a warmer atmosphere, we could see even more rainfall, for instance. Or let's say across Indonesia, we tend to see dryness during El Nino, and it's already a warmer atmosphere. That dryness could be even worsened because of climate change. So it's an interesting, it's a little bit more complex of a question than just naturally you normally think about it, but certainly the impacts from El Nino and La Nina can certainly be worsened due to climate change. But with that, I'll hand it over to you guys. You guys remember the two questions?
Yeah, do you want to answer the OA one?
So I can answer or speak to the first question to begin with. So she asked whether we as scientists can do our science and then actually turn that into something. So yes, it's still a little bit of a contentious issue, I would believe, in the scientific community, that scientists are allowed to still create good data and then actually advocate on some level to that. I believe it's something that we need to do, especially for problems like this. So there's two levels that scientists can do that at. We can speak to the public, which can begin to have small impacts in their everyday lives, such as perhaps driving cars less, flying less, and begin to reduce our carbon emissions. And then we can do something like on the policy level and begin to speak to people that can actually limit carbon emissions from the top down. And I think doing both of those are very important. Oh, can we undo oceanification? On a large scale, no. So it's unlike saving endangered species. We could breed them more in the zoo and then put them back, or we can plant more forests. In terms of oceanification, this is a global ocean problem. So perhaps in terms of like the oyster fisheries, where they can actually take them into the lab and grow them up to begin with, on a small scale, yes. And there's actually some recent research I saw come out that says we can actually do that for a coral reef. We can spend a lot of time and money buffering the water. In terms of for the whole ocean, no. We actually do not have the capabilities to begin to fix those problems on a large scale.
That's why we need a global climate agreement, so it's a global problem. But I wanted to take the upwelling question because I actually work in upwelling areas. Those are natural living laboratories that we work in. So upwelling occurs on the eastern side of ocean basins. So we have upwelling on the eastern Pacific, eastern Atlantic off of Africa, and then also monsoon-driven upwelling in the Indian Ocean. And so this upwelling actually brings up this very low oxygen, low pH water. However, this is very nutrient-rich water, and because of that, it fuels extremely productive fisheries. So where we see those really massive anchovy and sardine fishery, these are all upwelling areas. But just below the surface of the water, you have very, very low oxygen areas. And so as those low oxygen areas expand, it's causing these really productive fisheries at the surface to be compressed. So a lot of those aerobically active animals, they can't live under these low oxygen conditions, so they lose habitat. So it's this interesting dynamic between a very productive surface ecosystem and this upwelling that is driving that productivity, but then also this very low oxygen water right below it.
I'm going to try to address actually both questions. One, I believe, was about the pressure problem in the deep ocean. So measuring anything in the ocean is really hard because not only of pressure, because it takes a lot of energy to go all the way down and going up, and then send that information via satellite to a data center that we can then use to, validate our models or do what we call initial conditions. That's how you start your model with some knowledge about the climate system. And recently we've been developing some new floats called, they're called deep Argo floats, and they're developed at Scripps Institution of Oceanography, and there's some prototypes that can go all the way down to 6,000 meters. So 6 kilometers all the way down at the bottom of the sea, and they can survive the pressure. They're round. And if you go to the Argo website, argo.ucsd.edu, you can see some of those prototypes. They're very useful in terms of the energy budget balance of the planet, knowing how much warming the ocean actually takes up, because the ocean actually circulates, and in higher latitudes, like in the North Atlantic or in the Southern Ocean, there's a lot of circulation that goes all the way down to the deep ocean. So these floats and these instruments that can survive pressure are extremely important. And then regarding acidification, or really what scientists can do to find solutions, I think information is a very important part of the solution process. Not only how we fix, for example, acidification, but like what is the true impact of acidification on marine ecosystems? We talked about some of those impacts, but a lot of it is highly uncertain. We need to know what are the main ecosystems that are most vulnerable. Are there ecosystems that are going to gain from lower pH or lower oxygen? And so the dynamics are actually much more complex than a lot of the time that we want to think they are. And so it's really important to know as much as possible to have proper adaptation policies. And that's, I think, a huge role that scientists can be part of. Fixing acidification and deoxygenation and warming is really hard in the ocean. The climate system is very complex. Once you have an impact on pH, it's very hard to reverse that process because the ocean is very sluggish, moves slowly. Even though we see waves on the surface, it takes 1,000 years for the full circulation of the ocean to go through. So when we address impacts, especially here at the Conference of the Parties, we sort of think of them from a land lens, but the ocean has impacts that can stay on for a very long time. That's a unique perspective that we should keep in mind.
I just wanted to add one more thing about the role of scientists. One important role in the future will be monitoring our mitigation strategies. So how effective are our policies at fixing the problems? And Scripps, I know, has been doing a lot of work in the Gulf of California and with Hawaiian coral reefs to monitor how different strategies will actually solve our problems. And that's going to be a big role of scientists in the future.
Just to build on the idea of information, information is useful to a point. At some point in time, we need to transition that information into knowledge and into action. And a lot of times what that requires is the co-production of information. It can't just be a scientist talking to someone and saying, oh, you want to monitor the climate? Okay, I'll go do that and come back to you and tell you in a couple weeks what's going on. It really has to be an ongoing dialogue, and I think that's a huge change for the way the scientific community has been operating. Scientists can't just operate in labs anymore. If what they want to do is be part of the dialogue, they need to be at the table as well. And so this idea of co-producing knowledge, asking questions together, figuring out what questions can be answered and what ones are the right ones to answer, and then doing the research together so that there's trust in the results, that can address people's concerns about whether information is valid. It can help them feel invested in the solutions, and it really is the way that we've seen in the way our agencies funded science to make our science more influential.
Thank you for those comments. We have time for a couple of quick questions if there's any more out there. One here and one in the back. I'll do you two. Please introduce yourself.
Thank you. My name is Amadou. I'm from Mali. I'm particularly interested in the communication between scientists and policymakers. It's not an easy one, and I guess it can be different also depending on whether you are in developed country or in developing countries. But what do you think, from your experience, is the best way to have this communication taking place and effective, as you said? Thanks.
Thank you. I'm Sumaya Said from Sudan. You talk about mitigation. What about adaptation?
Thank you.
Okay, I can start, I suppose. So in reference to the question from Molly about science policy communications, I think that the issues that we are dealing with are complicated. They are sometimes have consequences that we don't understand, or maybe we don't understand where someone else is coming from. So I find that having really strong relationships with people and building communities of practice who are working together is a really important part about communicating science. If people trust you, they will trust what you are telling them more so, and they will understand why you're doing what you're doing, how you do it, and then that allows them to feel more invested in it as well. In regards to the question from the woman from Sudan, in relation to adaptation, adaptation is critical. We're already seeing impacts. We already need to change the way we do business. And I think that there's a lot the scientific community can tell us about different future scenarios, but there's a lot we can also learn from the science that's been done to understand current conditions and to understand what's being done with in response to El Niños. Many of the things that we experience from climate change, the impacts, are impacts that already happen. We already have floods. We already have droughts. The scientific community is working to better understand when those will happen, how they will change, but we have a lot of the solutions already because these are many phenomena that we're already comfortable with. And so I think a lot of adaptation is taking what we already know and applying it in different ways. There's still a need for much more science and much more research in those areas, but we do have a good foundation to start from.
Excellent questions from both members of the audience. I would say I was born in a developing country, but I'm a citizen of a developed country. And so my perspective is that we really need to build capacity in developing nations because they're going to inform adaptation strategies. They're going to be able to observe the coasts that are far away from international monitoring systems. And they're going to be informing policymakers' decisions in the future. And I think an important other aspect of policymakers, scientists communication is having programs like the NSF Interdisciplinary Graduate Research and Education Training, or centers like the Center for Marine Biodiversity and Conservation at Scripps. These are interdisciplinary centers that teach and promote communications education within scientists so that they can talk to people outside of their field in a sort of a regular language that people can relate to. And provide them with that information, provide them with that training, because it's really hard to have that training when you pursue a PhD, for example. You're working on a model or a lab or in a cruise. You're working by yourself most of the time. And so, your social skills have to be developed somehow to be able to talk to people. So having those programs, I think, are crucial for informing our way forward, I think, in climate.
Quick statement. We are running up against the time limit.
Okay, just a really quick statement. I would like to see the ocean science community engaged more, especially in developing countries, with helping provide information on what we need to be looking for. So again, coupling the global observations with the local observations that are really needed for adaptation questions, and using these case study examples like the one Kaitlin brought up in Washington and Oregon, where the way the aquaculture industry has now altered its behavior in order to deal with ocean acidification, so that we can really pass on these case studies to other countries.
Thank you for that, and I think this is a good place to end it. I think it's fair to say that a healthy ocean, again, is a healthy planet, but the problems facing our ocean are not small. These are large, complex problems that we'll have to face in the future, and we're facing right now. But I think what is clearly evident, though, is the passion amongst early career scientists. These are the people who are going to be out in the field or in front of a computer or working at the interface between policy and between the public and scientists, who will be helping communicate what the science is saying for our future. So I want to thank everybody here on the panel for a wonderful discussion, and I want to thank everybody for coming to the event and everyone watching online. So thank you.
And thank you for hosting us.
Thank you.
It was great.